The focus of this project is the development of a testbed prototype for the Quantum Permutation Pad, or QPP, which is a quantum-safe cryptographic algorithm. The prototype assesses the functionality of QPP in an end-to-end encryption and decryption system. It was developed using a Xilinx Zybo Z7 development board and programmed using Java, C++, and Xilinx high-level synthesis. QPP is a symmetric key algorithm that utilizes permutation logic gates to encrypt and decrypt data. The testbed serves as an efficient platform for assessing the effectiveness and security of the algorithm. Future development plans include the addition of AES-256 to enable a comparison against QPP and scaling the security parameters of QPP to enhance the algorithm's performance. The potential impact of this project is significant, as quantum-safe cryptography using QPP could greatly enhance the security of digital communication and data storage in various industries.
In this example, we're going to go through the encryption of their word hi using the predetermined matrix A and B. Here I say matrix is just an array that goes from 0 to the length -1. And then you permute the elements in it. So you see here we have an array of 4, so the numbers will go 0, 1, 2, 3. In each of the matrix that we have here, A represents a permutation of that, and B also represents a permutation of that. So first, the word hi is translated in ASCII code, which is 4869 in hexadecimal. The first step is we will convert it into bit stream. And then for each 2 bits of the bit stream, we will convert it into a number. So you see that we have 0, 1, which is 1, 0, 0, which is 0, 1, 0, which is 2, and this process repeated. And now we'll have a sequence of number 1, 0, 2, 0, 1, 2, 2, 1. We will use them to index the matrix AB alternatively. So you start with A, and then with B, and then with A again, and then with B. So we will index A with 1, and then B with 0, and then A with 2, and then B with 0, and the process continues. When we index these matrices of ours, we'll get a sequence of number again, 1, 3, 3, 3, 1, 1, 3, 0. For each of the number, we'll convert it into bit, and here we need to use 2 bits to represent them for each of them. So we'll get the sequence of 0, 1, 1, 1, 1, 1, so on and so forth. And now this bit stream will be converted to the final form 7F5C in hexadecimal. This is the encrypted string. To decrypt this thing, we just need to repeat every steps. So to say encode this word again, but this time we'll use the A and B transpose, which in this case happen to be also the transpose of, the inverse of A and B. In the end, you'll end up with 4869, which is the word hi at the beginning.
Now we are going to demo the integrated system. The node E will be a standard CPP program on host machine for simulation of the actual node E. In the later part, we are going to present the actual node E on Xilinx Zybo board via serial connection. The focus for now is to demonstrate how the command line interface works. And before that, we need the entire system running. So the first is to start with the core complex, as well as the node E and the command interface. The CLI is primitive and only presents the basic functionality of the system. By initialization, node E and the core complex will have handshake sequences and seed exchange. And then after that, we can say we want encryption to happen, and we want to encrypt the message hello. So this is the ciphertext of hello. Due to the input limit of the command line interface, ciphertext is too large to fit. It has to be read from a text file. Now if I want to decipher the message, I can say I want to decrypt it. Size of the text is 5. Hello is 5 characters, so 5. So this is the deciphered text. However, this is in hexa format. But we can prove this is a word that we want by using hexa to string converter. As you can see, this is going to convert it to the decoded string hello.
Alright, so I'm going to demonstrate the website components. So the first thing we're going to do is we're going to turn on the Common Core. And then we're going to turn on Node E. And then we're going to turn on the website. There we go. So if I retry again, we have the website booted up. So the website's booted up on localhost port 4996, and the URL currently we're on is index. Okay, so first page that you land on is the landing page here, and it gives a little brief description here, and there's the project design. It talks about the algorithm and the hardware and, you know, integrated system, conclusion, references, you know, all that stuff. So let's get to the more, you know, unique aspects. So first thing we're going to talk about is the automated test vectors. So you have your choice of algorithm, choice of test type, so encrypt or decrypt, that's what we're going to do. And you can choose what length you want, so I'll go, 100. Say number of tests, let's just go 1. And now let's submit this. Okay, so what do we get? Right, so we have a ciphertext, we have a plain text. So if I click on these two things, if I go to my downloads, these are the files that were downloaded, right? Compare the times, right? I'm not, you know. So this is the ciphertext. So this is the hexadecimal representation of the encoded, the encoded ciphertext in hexadecimal representation. And then this is our decoded plain text, right? So essentially what happened was that we fed in the random test vector into the encrypt, and then we got the ciphertext back, and then we took that ciphertext, put it back into the decrypt, and then we got the plain text, which is what this full file is. This has been encrypted and decrypted. Okay, it shows the test type, the algorithm, and the encrypt time and the decrypt time. Right, if we go back here and we go to file upload, this will allow you to upload any type of file you want to upload. Like anything will work. So right now we're just going to do test.txt. So in this text file, it just has a hello world exclamation point on it. So we're going to submit that. And okay, so we did our thing. So we're going to download the ciphertext and the plain text. So we're going to close these off and then open these up. And there you go. So this is the encrypted ciphertext that came from the receive encrypt function. And then this is our received decrypt plain text that we got back, right? So we fed in the file to encrypt it, and then we took our results from the encryption and we put it back in through decrypt, and then the plain text is this. So this has been encrypted and then decrypted. Okay, so that's kind of everything that there is to say with this page. So we're going to move on to demo. So demo is more of an interactive way of dealing with our project. So over here, what you can do is that you can type in and anything you want. So I'll type in hello world. If I click submit, so it will show you sort of in real time, if you will, the encrypted ciphertext here, right, in the block size that's determined in Node E, which is 2049 characters. And then we have our decrypted plain text, right? So first it encrypts it, and then it will take that, takes this, and then it will decrypt it, and then it shows you the times here for how long it took. So it took this amount of time to encrypt, and this amount of time to decrypt. All right, so that's all there is. You can do whatever you want here, right? So if I do like new lines and, whatever, you can kind of do whatever you want to, right? So it shows you the encrypted ciphertext, and then it shows you the plain text here, and this is how long it took to encrypt it, how long it took to decrypt it. So that's kind of it for that. So let's go to the interactive research tab. So in this will allow you to choose specifically encrypting or decrypting. Okay, so in this, in this section over here, you can type in, like before in the demo page, you can type in hello world, right? And you can submit it. And here you can choose to only run an encrypt test if you want to. So it gives you the time and it gives you the ciphertext, right? So now what you can do is that you can take your hexadecimal encrypted user input, you put it in here, right? And you put in the original plain text size, you submit, and then it will decrypt it and you can get a decrypted result, right? So an example usage here would be, let's take our ciphertext from earlier from the test vectors. So let's take it, let's copy it, put it over here. The original size was 100, submit, and there you go. So you have, this is our original thing. If we compare that with the plain text, they look pretty similar, right? They look quite similar. If you take a look, right, you can check if you don't believe me. Yeah, so there you go. That's the demo page, and API just kind of shows a list of the APIs, and then, we go back to the landing page, and that's pretty much it.
The Zybo board is currently connected to my PC, and I'm accessing the shell through a serial terminal in the bottom right. The core complex is running in the upper left terminal, while the CLI is running in the upper right. By starting a Linux process on the Zybo, I can begin to encrypt and decrypt data using the HLS kernel. I will enter the encrypt command in the CLI and enter the text hello world. The text is converted to an ASCII hex string by the CLI. The encrypted ciphertext is returned to the CLI. Notice the repetitive characters in the ciphertext. These are due to padding in the plaintext with no diffusion. This is the ciphertext that we from the original plaintext. By entering the decrypt command, we can see the original plaintext is restored. However, it is still in the format of an ASCII hex string. A custom IP core was created for the FPGA using a C++ program with Vitis HLS compiler directives. The HLS kernel uses a control-driven model, meaning it responds to control inputs instead of data inputs only, and it reads its data directly from memory. Here you can see the various control signals which are implemented as ASCII-like registers. The seed, permutation matrices, transpose matrices can be loaded. Decryption and encryption operations can also be started using the ASCII-like control registers. The HLS kernel is able to read and write data directly from main memory of the SoC without involvement of a DMA controller. It does so using memory-mapped ASCII interfaces. The interfaces are defined as parameters to the top-level function, and the interface type is specified using the HLS interface compiler directive. The encryption and decryption operations occur in the functions encrypt block and decrypt block. By using the HLS pipeline directive, I intended for Vitis to unroll the outer loop into 16 parallel execution units. However, the arrays that store the permutation matrices are implemented as block RAMs by default, which have a limited number of ports. So to synthesize, the synthesized report stated Vitis was unable to unroll this loop completely because of limited memory ports. I tried to avoid this issue by adding another HLS directive, array partition, to partition the permutation matrix array. However, this strangely resulted in the synthesized report stating a carry dependency error, and it was unable to pipeline the loop at all. To expand on this custom IP core, I would suggest using a pure HDL implementation rather than HLS, as HLS is better suited for data-driven algorithms. Here's a demonstration of the Vitis HLS simulation test bench successfully encrypting and decrypting data. The simulator CSIM compiles the program, runs the simulation test bench, and stores the results in a log file, which I will show shortly. Here we can see the plain text that was to be encrypted, the ciphertext, and the decrypted ciphertext resulting in the original plain text being restored.